For this problem, it says given x squared plus y squared equals 25, find y double prime, the second derivative, and then they want to know, would the line tangent to the curve at this point give approximations that are under or over estimates to the curve? Now let's pretend for a second that we don't know what this looks like. Okay. It asks for the second derivative. That's actually a pretty big hint if this was an AP problem. If they ask for the second derivative, they're saying concavity has something to do with this. So you can imagine that you start thinking about concavity. Okay, if something's concave up versus concave down. If it's concave up, we know that the lines tangent to the function are always below the curve, so they would yield an underestimate. If it's concave down, the lines tangent to the curve are always above the curve, so they will yield an overestimate. So the sign of the second derivative, which is concavity, which gives us concavity, will tell us the answer to the second question. So now let's say that we actually know what this is, because x squared plus y squared equals 25 is a pretty basic relation that you started learning about in Algebra 2, but this is a circle. X squared plus y squared equals r squared. So our radius squared is 25, so our radius is 5. At the point 0, 5, you're at the top of the circle, and the top of the circle will be concave down. So we should get a second derivative that is negative for this problem, and our estimates are overestimates. So step 1, take the first derivative. To get to the second, you start with the first. So the first derivative of this, x squared, is a 2x. And then I'm taking the derivative of y squared with respect to x, so this will be plus 2y dy dx. And then the derivative of 25 is just 0. The next step would be to solve for dy dx, so I'm going to subtract the 2x, move it over here, and then divide by the 2y. So 2y dy dx equals a negative 2x. And you can see I'm already starting to see a negative. That's kind of nice. It's comforting. And then I have divide by 2y, so dy dx equals a negative 2x over 2y, which when I reduce it is a negative x over y. Okay, that's our first derivative. We need our second derivative with respect to x, so we're going to do that implicitly as well. So we're going to take the derivative of this, which requires the quotient rule. So y double prime, or I'm going to write it the second derivative of y with respect to x using Leibniz notation. I'm going to write it like this so it's obvious. Equals the bottom function, which is just y, times the derivative of the numerator, a negative 1, minus the top function, the numerator, a negative x, times the derivative of the bottom, which is a dy dx, over the bottom squared, the denominator squared, a y squared. Now, you can't have a derivative inside of your derivative, but that's okay, because we actually know what dy dx is equal to. Our dy dx is actually just a negative x over y, so I can put this right there. So this will equal a negative y plus x, a negative times a negative x over y over y squared. So this is our second derivative of y with respect to x. You don't actually have to simplify this problem to know the answer, because it doesn't ask what's the second derivative in the most simplified form. It actually just says find the second derivative. We're going to go ahead and simplify it. So what you can do is actually get rid of this fraction within a fraction, and I'm going to do that by multiplying by a clever form of 1, which you look in the denominator, there's a y there that I want to get rid of. So I'm going to multiply by a y over y. And that gives you, when I distribute, a negative y squared, and then a positive x times a negative x is a negative x squared. The y's would cancel out. And then in the denominator, I now have a y cubed. Some people would move the negative to the denominator and make this a y squared plus x squared. It truly doesn't matter. It just depends on, if it's multiple choice, you just have to be able to identify it. Otherwise, you're fine the way it is. So this is our second derivative. The next part of the question says, okay, are the tangent line approximations underestimates or overestimates of the curve? So I'm going to take my point 0, 5 and plug it into the second derivative because I want to know about the concavity at this point. So the second derivative with respect to x when, and we'll say at this point 0, 5, is negative y squared, so negative 5 squared, minus x squared over y cubed. This is a negative 25 minus 0 over 125. This is less than 0. Therefore, the function is concave down. So I would say the tangent line would give overestimates of the function. And I know that because the second derivative is less than 0. And that is the end of that problem.